Just really quickly recap some of the ideas about refractive index. And we're going to start with the refractive index and how it relates to both the angles of incidence and angles of refraction. Now you can see on the screen here we've got a picture of a light ray moving from air into another medium. Okay. It's really key that we remember that, because the equations that we're using actually only really work when we're going from air into something else. Okay. If you study physics at a slightly higher level, you'll notice that there's a slightly different version of this of the equations that we'll learn, slightly more complicated, but still very relevant. Okay, so we're going from air into a medium. How do we know that? Well, we can see that we are bending towards the normal, and that means that we've slowed down, and that means that our speed has decreased. And usually we would assume that if we're going from air, that's the fastest speed that we can have. Speed of light is fastest in air or in a vacuum. If we want to calculate the refractive index, okay, the way we do this, well, one way we do it is we take those two angles, the angle of incidence, I, and the angle of refraction, R, take the sine of them, and then find the ratio of those two sines. Okay, so here we've got the angle of incidence in air or a vacuum, the angle of refraction in the medium, and N. And this N is what we call the refractive index. And really it tells us to what degree the ray has been slowed down by going from the air to the other medium. An example would be if the refractive index, say, was 2, then that would mean that the speed has reduced by a factor of 2. This is one way of calculating the refractive index, and all it is just using those two angles. Notice it's really important that we use the sine of the angles, not the ratio of the angles themselves. That's something that often trips people up. If we look a little bit more closely at refractive index, however, it actually has another equation which helps to define the refractive index. Okay, first things first, the refractive index is unique to each material. Okay, so glass and water, perspex all have their own refractive index. Okay. The way that we actually define the refractive index is by taking the ratio of the speed of light in the vacuum, c, 3 times 10 to the 8 meters per second, to the speed of light in the material, v. Okay? In other words, n is equal to c divided by v. I'll say it again, c is the speed of light in the vacuum, and v is the speed of the light in the medium or in the material. Now you notice here, what we've said, in the vacuum, the speed is always at its maximum. That means that if we go from air into the material, we're going to slow down. And so therefore, my n is always going to be a number greater than 1. We never, ever have a value which is less than 1 for our refractive index, certainly at GCSE level. Okay, now if we look at the diagram, what you can see is the effect of that slowing down. We said before that when we go from fast to slow, our wave slows down and therefore bends towards the normal. Okay, and then as it goes from slow to fast, as it emerges from, say, our glass or perspex box, we'll see it bending away from the normal. That's what this wave is doing here. Now, what's interesting here is that this drawing also demonstrates the effect of refraction on a wavelength. That's really a key point, because if speed is changing, then wavelength might change as well. And what you can see here is if we go from the fast to the slow, those wavelengths are actually getting shorter. And it turns out, if we define our wavelength as lambda A and lambda B, actually my refractive index, as long as I'm going from air into a medium, is simply the ratio of the two wavelengths. So this is a third and slightly less common equation for the refractive index. Not only is the refractive index the ratio of the speeds, so the speed in A to the speed in B, or the speed in the vacuum to the speed in the material, but also the ratio of the wavelengths. We've gone from a large wavelength to a short wavelength. Key in this is the fact that the frequency never changes. So as my wave travels from the air into the medium and then back out again, the frequency is always the same. The two quantities which change are the speed and the wavelength. The reason I'm sort of highlighting these in this video is because these are points which are often missed by students. We often learn the equation, for example, about the ratio between the speeds. However, we don't tend to think about the effect of that on the wavelength. And what you can see quite clearly here is that the wavelength is getting shorter. And the reason for that really is the fact that the frequency does not change. As usual, add this to your notes and ask any questions if you're not sure. I'm always happy to help. Thanks for watching.